Welcome to the Unit 14 Section 1 video on absolute value characteristics. An absolute value function is a function that contains an algebraic expression within absolute value symbols. Recall that the absolute value of a number is its distance from zero on the number line. When presented with the absolute value of a number or monomial, that term becomes positive. So for example, the absolute value of -5 is positive 5. The absolute value of negative x is positive x. The absolute value of 7 is 7. The graph of the absolute value parent function is composed of two linear pieces joined together at a common vertex. And in the case of the parent function, that vertex will be the origin. So let's take a look at the parent function for an absolute value function. The parent function is f of x equals the absolute value of x. So if x is -3, you put -3 into the absolute value symbols and you will get 3 as your output. The absolute value of -2 is 2. The absolute value of -1 is 1. The absolute value of 0 is 0. The absolute value of 1 is 1. The absolute value of 2 is 2. And the absolute value of 3 is 3. So if you were to plot these points and sketch a graph, you would get a graph that looks like this. And that graph is in the shape of the letter V. Let's take a look at some of the key features of the parent function for absolute value functions. Now you're going to notice some similarities here between a quadratic function and the absolute value function in terms of the key features. Most notably, the fact that both an absolute value function and a quadratic function have a vertex. And the end behavior is going to be similar as well. So let's start with the x-intercept. The x-intercept here would be 0, 0. That is the point at which we touch the x-axis in this case. If this graph were a little bit lower, if it were to be pushed farther down, then you would have two x-intercepts. If it were to be shifted farther up, you would have no x-intercept. The y-intercept in this case would also be 0, 0. That's where we cross the y-axis. The domain is -∞ to +∞ because we have an arrow on the left and an arrow on the right. The range would be 0 to infinity because the lowest value that we have for y is 0, and then the graph moves upward from there on both ends. The absolute minimum would be 0, 0. There is no point lower than 0, 0 on this graph. The slope would be plus or minus 1, depending on which side of the vertex you're on. The slope is -1 on the left side of the vertex. It's +1 on the right side of the vertex. The positive interval would be -∞ to 0, union with 0 to infinity. So every point on this graph, other than the vertex, is positive. We have no negative intervals. We are increasing from 0 to infinity. That's on the right side of the graph. We're decreasing on the left side of the graph, -∞ to 0. And our end behavior, as x goes to infinity, f of x goes to infinity because it's pointed upward on the right side. And as x goes to -∞, f of x goes to infinity because it's pointed upward on the left. Any absolute value function with a slope other than plus or minus 1, a vertex other than the origin, and or opens downward is simply a transformation of the parent function. So let's take a look at this familiar table. Our absolute value transformation rules stem off of f of x equals a times the absolute value of the quantity x minus h plus k. So if we have h as positive, we have a translation to the right. This would be notated by a minus sign because in this case 3 is positive, but it follows the minus sign in the form x minus h. So x minus 3 in the absolute value function would indicate a translation to the right by 3 units. A translation to the left occurs when h is negative, so we have the absolute value of x minus -3, which looks like the absolute value of x plus 3. We have a translation up when k is positive. So in this case, the absolute value of x plus 5. And a translation down when k is negative. Absolute value of x minus 5. The reflection across the x-axis occurs when a is negative. So you would have a minus sign out in front of your absolute value sign. A reflection across the y-axis occurs when x is negative. So your absolute value of negative x. The negative would be in front of the x, but inside the absolute value symbol. You have a vertical stretch when a is greater than 1. So your value in front of the absolute value symbol would be greater than 1, such as 2 times the absolute value of x. And then you would have a vertical compression when you have a between 0 and 1, so such as 1/2 times the absolute value of x. So in this case, your stretch and compression value would be your slope on either side of your vertex. Negative on one side, positive on the other. So let's identify the transformations that occur to the absolute value parent function. You're going to find this is going to be very similar to the transformations we've already done, most notably very similar to the ones we've done with quadratics. So in A, we've got plus 3 inside the absolute value symbol, so that is a translation to the left by 3 units. And then we have a minus 2 on the outside, which tells us that we moved down 2 units. In B, we have a negative in front of the x inside the absolute value, so that's a reflection across the y-axis. And then we have a plus 4 on the end, so that tells us we were translated up 4 units. In C, we have 1/2 out in front, so it's a compression to a slope of plus or minus 1/2. And we have a negative 7 inside the absolute value, which tells us that we're translated right 7 units. In D, we have a negative out in front, so we have a reflection across the x-axis. We have a minus 2 on the inside of the absolute value, telling us that we are translated right 2 units. And we have a plus 5 on the end, telling us we're translated up 5 units. In E, we have a vertical compression to a slope of plus or minus 1/4. We have a translation to the left 1 unit inside that absolute value symbol, and then we have a translation down 1 unit indicated by the minus 1 on the end. And for F, we have a minus out in front, so we're reflected across the x-axis. The 2 tells us that we're stretched to a slope of plus or minus 2. We have a minus 3 inside the absolute value, so we're translated right 3 units, and then the plus 8 on the end tells us we're translated up 8 units. Now let's write an equation for a graph of the given function. So in A, we have a translation to the left 5 units, so that tells us that we have to have a plus 5 inside the absolute value symbol. So f of x equals the absolute value of x plus 5. For B, we're clearly reflected across the x-axis because we are pointed downward now, and we are translated up 4 units since the vertex has moved up the y-axis by 4 units. So we're going to put a minus out in front of the absolute value, and we're going to put a plus 4 on the end. In C, you can tell that we are compressed, so we take a look at our slope. We have a rise of 1 and a run of 3. So we have a compression of plus or minus 1/3. We are translated down 6 units because our vertex moved down the y-axis by 6 units. So we have 1/3 times the absolute value of x minus 6. For D, our slope is 2 over 1, which is 2, so we are stretched to a slope of plus or minus 2. We are shifted to the right 3 units, and we are shifted down 3 units. So we have 2 times the absolute value of the quantity x minus 3 minus 3. For E, we are reflected across the x-axis since we are pointed downward. We are not stretched or compressed because our slope is still 1. We also have a translation to the left 3 units and a translation up 5 units. So we have negative the quantity of the absolute value of the quantity x plus 3 plus 5 on the end. And then for F, we are stretched to a slope of plus or minus 3, and we are shifted downward 7 units. So we have 3 times the absolute value of x minus 7. In this example, we want to graph each function and identify the given key features. So f of x equals negative absolute value of x plus 1 plus 3. So we are going to identify that we have a reflection across the x-axis, we are shifted to the left 1 unit, and we are up 3 units. So we're going to have our vertex at the point negative 1, 3, and then we're going to graph our absolute value downward with our slope of 1. Now let's identify the domain. The domain is negative infinity to positive infinity because we have an arrow on the left and an arrow on the right. And our range is negative infinity to 3, since the highest point on this graph is y equals 3. Here we have this function, which has a vertical stretch to a slope of plus or minus 3. Our h value is 2, and our k value is negative 4. So we're going to plot the point 2, negative 4, and then we're going to do our slope of plus or minus 3, making sure our graph is opening upward, since it's not reflected. The y-intercept is at 0, 2. The increasing interval is from 2 to infinity, and our decreasing interval is negative infinity to 2. Now let's do an application problem. During the winter holiday sales, target sales steadily increased over the holiday weeks. After the holiday, the sales started to decline. The following function represents the amount of sales per time t in weeks. Find the average rate of change over weeks 1 through 5. So to do this, we're going to plug in 1 for t to find out what our output is. So we're going to solve this. The absolute value of negative 3 is 3. Negative 2 times 3 is negative 6. And then negative 6 plus 4,300 is 4,294. Plug in 5 for t. 5 minus 4 is 1. The absolute value of 1 is 1. Negative 2 times 1 gives us negative 2. And you add that to 4,300 and you get 4,298. So that gives us our x1, y1 and our x2, y2, which we can then put into our average rate of change formula, y2 minus y1 over x2 minus x1. And that's going to give us 4,298 minus 4,294 over 5 minus 1. That gives us 4 over 4, which is 1. So what this tells us is that the rate of change over weeks 1 through 5 is that we had our sales increase by 1 every week. So it was a steady climb of 1. Thanks for checking out my video in the Algebra 1 Honor Series. You can subscribe to my channel. I've got the next video queued up for you. And if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.